We've been symbolizing vectors by putting a little arrow over whatever was a vector, and we've been thinking about them as something that has a magnitude and a direction. Magnitude and direction. The magnitude, we've been using the absolute value of the vector, and direction, we've been saying it's in the positive or the negative direction. There's another way to think about vectors, but first let me draw out the vector. So there is our vector, it's in purple. The magnitude is the length of the vector, and the direction is, well, the way it's pointing. But if we put this guy on a coordinate system, so I'll draw in the x-axis and the y-axis, and x and y are always 90 degrees or orthogonal to each other. That's important. If I draw in the x and y, now to get the direction, you can actually measure it from the x-axis, or any other axis you want to, but usually we do it by convention counterclockwise from the positive x-axis. So now there's our direction. So in addition to positive and negative, we also get an angle, because we've gone into 2 dimensions. We can go to 3 as well. But magnitude and direction, that gives us our purple vector. But now we can think of it in terms of how much of this purple vector is in the x direction and how much of it is in the y direction. So if I draw that out, well, I can pretend I'm shining a light down this way, and my vector will cast a little shadow, and the shadow will be this length along the x direction. So I can say that is a sub x, or the amount of the a vector, which is in the x direction. And then next, I can pretend I'm shining a light from this way, and my vector will cast a little shadow onto the y-axis. And the shadow will be that long, and I can call that a sub y, or the amount of the vector a, which is in the y direction. And that gives us a new way to think about vectors as components. So that would be the amount of the vector that points in the x direction plus the amount of the vector that points in the y direction. And then if we need it, we could also add in the third, or z direction. So you can think of a vector as magnitude and its direction, that's in blue, or you can think of it in terms of its components. It's x, y, and z piece. And if we're going to write out the vector in terms of these, we have a special way of doing it. We have our vector A, and in terms of components, it's equal to the sum of its x piece, its y piece, and its z piece. But these guys aren't just scalars, that is, they aren't just numbers. Direction is also important, so we need a way to symbolize in the math that you just can't add up this number plus that number plus that number. And to do that, we use unit vectors, or I hat, j hat, and k hat. And these guys are what's called unit vectors, and what that means, well, I hat just means x direction. So this is just a way of saying it's this much in the x direction, and then j hat means y direction, or it's a sub y amount in the y direction, and k hat, of course, is the same thing just for the z direction. And sometimes instead of I hat, j hat, and k hat, you might see x hat, y hat, and z hat. And the hat just symbolizes this is the unit vector, this is the guy that's telling me only about direction. And it doesn't matter which convention they use. But I'm going to go ahead and use I hat, j hat, and k hat here. So that's how you write it, saying you can't just add these numbers up because they're all in different directions, different orthogonal directions, 90 degrees from each other. Okay, so how do you get from the component way of thinking about vectors to the magnitude and direction way of thinking? For that, we're going to want to redraw the length of the vector, the angle, and these 2 components. And you might note this kind of looks like a triangle, and that's really the key here. So I'm going to redraw my vector. There it is in a purple arrow. The length of it is still the magnitude. There's still the angle here. I'm going to redraw AX. There it is, AX, but I'm going to take AY and I'm going to move it over to this side. So there's AY, and now you may see we have a right triangle. So that means everything we've learned about trig we can bring back and use. So hopefully you remember that the sine of an angle when you've got a right triangle is equal to the opposite side, this side on this particular triangle, over the hypotenuse of the triangle, which is the long side. In this case it's our magnitude A. And that the cosine is equal to the adjacent side, so the side closest to the angle, over the hypotenuse. And now we can plug in, for this particular example, we can plug in what the opposite and the hypotenuse are to get from direction to coordinates. So the sine of the angle is equal to, well, the hypotenuse, that's the length, so that's our magnitude. We got direction and magnitude, but the opposite, the side opposite the angle, that's AY. That's a component, so we can rearrange this, multiply by the hypotenuse, or the length of the vector, and we'll get the y component of this particular triangle is equal to the hypotenuse, or the magnitude of the vector, multiplied by the sine of that angle. Won't always turn out that sine and AY are associated. You have to draw the triangle and think about the opposite and the hypotenuse. But in this case, that's what it is. Something similar will happen for cosine. So the cosine of the angle, oops, I forgot to write it in here, is equal to the adjacent side, that'll be AX here because it's adjacent to that angle, over the hypotenuse. And the adjacent is my AX. I'll rearrange these guys to get the x component of my vector is equal to the length of the vector times the cosine of that angle. So we've gone from magnitude and direction to the components. And we can go back the other way as well. So instead of sine and cosine, now we're going to need to use trig. Remember, tangent is equal to the opposite over the adjacent side. So tangent doesn't have the hypotenuse in it, but for this particular triangle, we'll have tangent of our angle is equal to the opposite, that is AY for this particular triangle, over the adjacent, that's AX for this particular triangle. So if we want to find the angle and we know these components, we can then solve for theta. So theta equals arc tangent of AY over AX. And sometimes you'll see this spelled out as arctan, so spelled out like this, arctan. Sometimes you'll see it as tangent to the -1. I don't really like that because it's a little confusing with powers, but I'm going to use atan for arctan. Just means the thing that undoes the tangent. So that's how we get the angle. To get the magnitude, we have to add things in quadrature. So what that means is we're looking for the magnitude, we're looking for the hypotenuse, and it's equal to the square root of this side of the right triangle and that side of the right triangle squared. You might, of course, heard this called the Pythagorean theorem. In physics, we've expanded it out, and it is adding things in quadrature, which just means you square them, you add them up, and you put them under a square root. So that's how you get from the component way of thinking about a vector to the magnitude and direction way of thinking about a vector.